Okay, so now we are going to get into some heavy stuff. We're going to look at series AC circuits and how we apply all of that right triangle and complex number and reactance relationships to AC circuit analysis in series circuits. So, in every case, we're going to look at the different values that we've been used to using: voltage, currents, now phase angles, and resistances, reactances, impedances. All of these things are all coming together now on a pretty grand scale here. So we're working through all of those chapters, all of that math, and all of those applications to come up with those relationships. So we're going to look at using the trigonometric functions, expressing phasors as polar and rectangular, doing series RC and RL circuit problems, adding and subtracting impedances, and then finally we're going to end up in resonances and resonant frequencies. So in series RC circuits, in a series circuit, we use the letter I, the current, as the reference in our diagrams. In an RC circuit, current leads, so the voltage across the capacitor and the reactance in the capacitor are plotted along the negative y-axis, or that negative j-axis. The applied voltage E, or the total impedance Z, becomes the hypotenuse of the right triangle, or our resultant vector or phasor, and theta then becomes the phase angle. We have to keep track of whether that angle is positive or negative, because it will affect which quadrant we're going to be in. Capacitance in AC circuits causes the current then to lead the applied voltage. So as you look across the bottom of the page here, the schematic diagram for the simple RC circuit, and then two different phasor diagrams or vector diagrams. One, it maps the current, the voltage across the resistor, and the voltage across the capacitor. And the other one maps the totals of resistance and X sub C for our total impedance Z. So we've got two different diagrams here that we're plotting our characteristics on. So the things to remember then is that the voltage across the resistor here lies on the x-axis, and it is the adjacent side to the angle formed theta, and that of the voltage across the capacitor. Okay, that becomes the opposite side. Okay, so that becomes a projection. Doesn't look like the opposite here, but it's actually a projection from the minus j-axis all the way out here. We could actually move it right there. So the current leads the voltage drop across the capacitor by 90 degrees. So there's a lot of examples in this text, and I'm going to go ahead and go through all of them, because the more we practice them and the more we're exposed to them, the more it's going to make sense to you. So in every case here, they're going to give us some values, and we are going to apply them to the relationships. So if we let the voltage across the resistor be a 10-volt drop, and the voltage across the capacitor be a negative 12-volt drop, they want us to find E, the applied voltage, and the angle theta. So now we go back to using those trigonometric functions as they relate to the sides of the triangle. So in setting this up, the first few times they'll lay it all out for you. The opposite side divided by the adjacent side. Okay, so here is our opposite side. Here is our adjacent side. So we're actually taking the two phasors that form the voltage drop across the capacitor and the voltage drop across the resistor to form a ratio that becomes the tangent of theta and the actual angle. Okay, so the voltage across the capacitor, they gave us minus 12. 10 volts across the resistor gives us a minus 1.2. Okay, so that ratio gives us the tangent of the angle, not the angle, but the tangent of the angle, minus 1.2. So in looking at this, then I need to take the inverse tangent of that tangent value, minus 1.2, and that becomes the angle theta, or a minus 50.2. So since it's telling us a minus, we must be projecting the angle down or laying down the resultant here in the negative direction. We're actually going to go clockwise from the x-axis down, and that gives us minus 50.2, which is indicative of a circuit that has a capacitor in it. Okay, it's always on the minus j. The positive j-axis is indicative of an inductor. So now we're going to switch gears. We switch to the sine function. You'll see this a lot. You'll have to look and see, of the pieces that you're given, how can I calculate for my values so that I can hit my target, in this case, that E value. So the sine of theta is the opposite side over the hypotenuse. Okay, so we know that we have the voltage across the capacitor, but we still don't have the hypotenuse. So what we're going to have to do is we're going to have to take that expression, sine theta is equal to the voltage across the capacitor divided by the applied voltage, and we're going to have to rearrange it. We're going to have to move terms around, because what we want to solve for is that unknown E. Okay, so E is the applied voltage. If I move E into the numerator, move sine theta into the denominator, I get the expression VC over sine theta is equal to minus 12 volts divided by the sine of minus 50.2, which we calculated up here in the first block. So the sine of minus 50.2 is a negative 0.768. Divide that into negative 12 volts, and we get a positive 15.6 volts. So that ends up being the length of that phasor or that vector. So now we can see here that we actually have the two components of a rectangular relationship, 10 and minus 12. We can put that into the rectangular form then as the total for E is equal to 10 minus J12. Okay, so in this one here, we see we had just a couple of unknowns that we needed to solve for so that we could get the entire relationship displayed. Okay, let's look at a different one here. Now we're given the value of E, which is the vector here, the resultant, and we are given the voltage across the resistor of 18 volts. They want us to calculate for the voltage across the capacitor and theta. Okay, so let's start with a trigonometric function where we have values that we know, V sub r and E. We have the source, 25 volts. We have the drop across the resistor, 18 volts. So we set up the ratio. The cosine of theta then is equal to 0.72. Now we apply that inverse relationship so that we can solve for the angle theta, which is the first term that they asked us to solve for, and we end up with a theta of minus 43.9. Again, a negative angle where we go clockwise from the origin, minus 43.9, and again it's indicative of it being a capacitive circuit. So now we switch to the sine of theta so that we can set up an equation for finding the unknown V sub C, the drop across the capacitor. Again, having those, we can rearrange our terms to solve for V sub C, and what we're going to say now is E times the sine of theta is equal to 25 volts times the sine of minus 43.9, which gives us a minus 17.3. Again, indicative of a capacitive circuit. It's laying right on the negative J axis. Okay, so before we go into section 2 here, where we start applying the reactance formula, let's go ahead and stop here and move on in the next video.